In the last lesson, you saw how we can quickly code up a physically realistic simulation using some basic concepts of motion and some basic physics, such as conservation of momentum from collisions. So now let's review some of the physics you'll need to know for this course by starting with vectors and looking at concepts of motion like the relationship between position, velocity, and acceleration. And we can represent all of these quantities with vectors. So just as a reminder, a vector is a way of representing an object that has both magnitude and direction. This can be something like its location. So for example, in our last lesson, we had a ball that was located a certain distance from the center, and we basically said that there was a vector position of 0, 10, and 0, which said that it was a ball that was located 10 units from the center of the screen in the y direction. Anything which has direction and magnitude can be represented as a vector. It could be its velocity. So for example, the ball, when its velocity, as it started to fall, the velocity was down, and it was originally just whatever the old velocity was plus our acceleration times time. And that was a vector quantity pointing down, which told us how fast the object was moving, and we described that in the code as a vector. Our acceleration was also a vector. That acceleration was pointing down with minus 9.8 meters per second squared, and that was represented again as a vector in the y direction. So you can represent this as, in the code we said it was a vector which had components 0, minus 9.8, and 0. So those are vector quantities for position, velocity, and acceleration. So anything with a direction and a magnitude can be represented as a vector. Now there are a number of ways we can mathematically represent a vector. One of these ways is that we can specify its length. So that would be its magnitude. So let's say this is a vector A, and the vector A has a magnitude. Its magnitude is given by the absolute value of that vector's length. So that would just be this right here. This length right here is the vector's magnitude. And then the direction can be given by the angle from some axis. So in this case, this is the x-axis. This would be an angle here. We could call that theta. And in this case, it looks like theta is something like 30 degrees from the x-axis. So we can use the length of the vector, which is just a scalar quantity, and then the angle from the x-axis. The other ways that we can represent a vector is by the components in some coordinate system. So typically in our VPython, we have a coordinate system that looks like this. We have the up and down, this is 3 dimensions, this is the center of the screen. The up and down is the y dimension, the back and forth is the x dimension, and the front and back is the z dimension for the VPython coordinate system. And we can specify a vector quantity anywhere in here where we can just say, well, it has these components, and those components would be the position along the x-axis, the position along the y-axis, and the position along the z-axis. And I can draw a line from that, and in 3 dimensions that would look like this. So there's our little vector there. And we would write that vector, let's say that's a vector A. That vector would be written as the coefficient of the length in the x dimension plus the coefficient in the y dimension plus the coefficient in the z dimension. And these little hats here, these are all unit vectors on the x, y, z. So we call those unit vectors because they have a length of 1. So the unit vectors are just telling us the direction. The A, B, C are telling us how far to go in those directions. And so in this case, we would go A in that direction. We would go B in that direction. We would go C in that direction, and that would give us this vector right here. And in general, in computational physics, we use this type of Cartesian coordinates in a flat geometry, like a Cartesian Euclidean geometry for our vectors. So in computation, we really are typically thinking about our vectors in terms of the x, y, and z components. And when we saw, you saw this come out when we were checking with the collision with the floor, because we could reference the ball had a position in the y dimension. Right? So we can say the ball, which is our object in question, the position is the vector, and then we can pull out just the y dimension, and then we check to make sure that that was less than the floor's y dimension. So we typically think of vectors as x, y, z quantities, and we can draw those in 3 dimensions. Now, once you have a vector, there's a bunch of things you can do with it. Right? You can add and subtract vectors. And you probably remember from your physics classes that we can do that graphically. If you imagine here, we'll just do this in 2 dimensions to keep things easy to draw. So let's say you've got a vector you've got 2 vectors. You've got vector A and you have vector B. And you ask, what is the sum? What is the addition of those 2 vectors? Well, graphically, we can do the tip to tail thing where we take B and we sort of detach it from this point and we put it over here and we draw it with the same magnitude and direction. And then we draw a resultant vector from the origin to the tip of that vector, and this would be our A plus B vector. Right? That's our sort of graphical way of doing that. Subtracting 2 vectors is pretty similar. You can have our vector A. We'll take this 2 vectors here, and then you have our vector B, the green, and you ask what is the the difference between these. Well, you say A minus B would be, so A minus B is the same as A plus A minus B. So when we minus a vector, that just reverses its direction. So we can take and put B here, that would be minus B, and then that means the resultant vector is down here. That's going to be our A minus B. So you're probably familiar with doing these things graphically in your physics classes, but it would be nice to know how do you do this mathematically in our code. So to add and subtract vectors in the code, we can just add and subtract components. So you could write A plus B as being the same as our AX component and our AY component added to the BX component and the BY component. So that's the same vector as AX plus BX and AY plus BY. And if you think about how we were doing that in the code in the last exercise, that would be the same as doing our ball dot position dot x, and you could add the floor's position dot x, and that would give you the new x position of the sum of those 2 things. And we can do subtraction the same way. You just subtract components. So that's adding and subtracting vectors. The second thing we can do, operation we can do to vectors, is we can multiply. And we can multiply in a bunch of different ways. We can multiply by a scalar. So that would be like taking, let's say, a constant c and multiplying it by an vector a. That would be the same as taking c times ax and c times ay. So that would be multiplying by a scalar. We can do something called a dot product. And a dot product is when you have 2 vectors. These are operations on 2 vectors where you have a vector A and a vector B. And when we do the dot product of these things, A dot B, that's the same as adding the sum of their components. So I can say AX BX plus AY BY. And this is effectively giving you a new vector where these 2 vectors are projected onto one another. The other thing that we can do is something called a cross product. I'm not going to go through this one because it's a lot of stuff to write down, and you can look this up, but the cross product is basically a way of multiplying two vectors together to where you get another vector which is perpendicular to those two, and you can write that down as AB times the sine of the angle between them, and then the direction is going to be in whatever direction is perpendicular to A and B. And there are a number of ways to do that computationally. Luckily, Python has built-in libraries for doing these calculations for us. So we'll see these things come across. If you remember from your physics, cross products show up in angular momentum. They show up in magnetic fields. They show up in a number of places. Dot products happen whenever we're projecting components onto an axis from an angle. And then scalar products happen anytime we multiply a vector by some scalar quantity. Okay. So that's just a brief reminder of what vectors are and how we operate on them, but what's more important is how they're related to position and velocity. So we've already talked about our coordinate system in VPython, where we have, x and y is going to be going in the left-right direction, y is up-down, z is front and back out of the screen. And those positions, velocities, and accelerations are all going to be relative to this coordinate scheme. But how are position, velocity, and acceleration related to each other? So if we think about it, let's first start by drawing, imagining our ball here. We had our ball that was dropping with some acceleration. And the question is, what is its motion going to look like? What is its acceleration going to look like as a function of time? What is its velocity going to look like as a function of time? And what is its position going to look like as a function of time? So let's start by imagining a graph of acceleration as a function of time for a gravitational field. And if you think about it, the gravitational field is constant, so we just get a straight line like this. Now, what does that mean if we've got a straight line like this? Well, that means that the change in velocity is just going to be the acceleration times our time interval, right? So in other words, we have a linear relationship between the change in velocity and the acceleration. And so that means I can draw how the acceleration is going to look by drawing that linear relationship. So I can draw how the velocity is going to look by drawing that relationship. So the velocity as a function of time is going to be a line, and that line, the slope of this line is, you guessed it, the slope of this line, you guessed it, is going to be the acceleration. And so these are related to each other. The slope of the velocity curve is the acceleration. Now you'll notice that this is a constant slope, which is a constant here in this line. But if I ask what's happening in terms of position, if I ask what's happening in terms of position, as an object falls through space, its position gets further and further away from where it started, faster and faster and faster, because the velocity is getting faster and faster and faster as we go. And so that means that the position is going to have this kind of hyperbolic curve to it. And that's because the slope at any one point on here is the velocity. So if I imagine a tangent line to some point here, that is the velocity here. So the slope of this line is the velocity. And we can represent all of those things with mathematical derivatives. So we usually say that we have given our position, that the time derivative of the position is equal to velocity, and the time derivative of the velocity is equal to the acceleration. And you can flip that around, and you can also say that the the velocity, the accumulated change in velocity is going to be the integral of the acceleration, and the accumulated change in position is going to be the integral of the velocity. But these right here represent differential equations, which is where we got the solutions to our first simulation that we had in the very first lesson. Because if I think about this type of equation right here, let's go ahead and clear the screen and just look at that in detail. We have an equation that says that if I know the acceleration, I know the relationship between the change in velocity and the change in time. And I can solve this equation by just separating out my position and time and integrating both sides. And when I do that, I get that the velocity is equal to some starting velocity plus my acceleration times time. And this was the equation that we used to compute the new velocity from the acceleration and the old velocity. And you can do the same thing with the position versus time as well, and you wind up getting our position is equal to the old position plus the velocity times time. So this is really handy because it gives us a very quick way of doing evolution in time. And in reality, you don't need to bother with doing this integral because we're doing things on such a small time step that if we just advance this by some small amount, we can treat all this as linear and we can compute almost anything we want. Okay, so now that we've seen that the differential form of time, position, velocity, and acceleration are related, we know that if we know the acceleration of an object, like in our ball drop example, we can compute the change in velocity and we can compute the change in position, and that allows us to model its motion. Of course, we need to know how to figure out accelerations, and that for that we need forces, but that is the subject of the next tutorial. See you there.